all of this information. So we're going to have the integral from 0 to 1, x squared, well that's going to be 4t squared, and then we have z, which is 6t minus 1, and then we have this square root, so we'll have 4 squared plus minus 5 squared plus 6 squared dt. So the square root, thankfully, is not going to complicate things because it's just going to be square root of a constant. Okay. So what we get here, this is going to turn out to be the square root of 77. So let's pull it out. And then we'll have 16t squared times 6t minus 1. Alright, multiply it out so we get 96t cubed. Actually, what I'm just going to do, I'm just going to pull the 16 out also, just to keep the numbers down. So now we have 6t cubed minus t squared. Okay. Alright, so then I trust you guys can finish it off from there.
Not a problem.
Okay. Well, I'm a little more concerned about everyone else here.
That's showing favoritism.
All right. But as with what we were doing in the previous chapter, the key is, are we getting the setup right? So any questions about the setup? So you get your parametric representation of your curve if it's not given to you already. Use that to plug into your function, x of t, y of t, z of t. Derivatives go in here. And then whatever you get, integrate in the usual way, no matter how easy or difficult that may be.
This is just called evaluating line integrals?
Yes. Yeah, that's it. All of these we're dealing with are line integrals. Anytime you're integrating over a curve. So, which is kind of odd. You think it's called a curve integral.
Yeah.
But whatever. Once you parameterize it, you're integrating over a line, you're integrating over an interval. But now let's do another where a different kind of curve where the integral itself turns out to be a little more challenging. 2x plus 9z ds, where this time the curve defined by these parametric equations. So x is equal to t, y is equal to t squared, z is equal to t cubed. And t, once again, runs between 0 and 1. So we need our derivatives. So we have 1, 2t, and 3t squared. So now we can plug in x in here and our z in here. And since we're integrating with respect to t, we'll go from 0 to 1. So we're going to get 2t plus 9t cubed. And then ds is going to be x prime squared plus y prime squared plus z prime squared. So now we'll fill in what that is. All right, so x prime, that's just 1. Then we have 2t squared, so that's 4t squared. And then we have 3t squared quantity squared, so that would be 9t to the 4th. Okay. All right, So now that is what you're going to integrate. A little uglier. But if you decide to try a shot in the dark, see if a U substitution is going to save you. You can try finding U to be this. So U is going to be 1 plus 4t squared plus 9t to the fourth. So then du is going to be 8t plus 36t cubed dt. And looky that.
Look at that.
So that is 4 times that. So
Damn, I wish I could take stabs in the dark like that.
yeah. Because real problems always work out this way. But that's why for real problems they just forget all the stuff and do it numerically.
Yeah.
Okay. So for convenience, I'm going to pull out, since we see that this is 4 times this, I'm going to pull out a factor of 4. So now du over 4 is exactly the factor we're trying to get rid of. So now we get these things to match, just to cut down on a chance of making a careless mistake, like what might happen in the middle of an exam. So now what we're going to get is integral of 1/4 u to the 1/2 du of what we need limits. So when t is equal to 0, we'll plug t equals 0 in here, we get u equal 1. We plug in t equal 1, is it's going to be the sum of the coefficients. It's 14. So those are your limits in your modified integral. So now you can polish this off. So we have 1/4, 2/3, u to the 3/2, evaluated at 1 and 14. So we get 14 to the 3/2 minus 1. All that times 1/6, and that's your line integral. So in this case, you're given a parametric representation. So get your derivatives, form this factor, plug in x to t, y to t, z t into your function, and then hope you get something you can do. All right. So questions on either of these? Okay. Now, so this is the case where we're taking a scalar valued function and we're trying to integrate it over a curve. But now, if we go back to the original application we were talking about, and that is computing work. So go back to something that was discussed a little bit in Calc 3. Well, I think it would have been on the day that Dr. Koloval subbed. So I have no idea if he actually talked about it or not.
I actually skipped that day.
Yes, but specifically about work involving a vector valued force. So, and I know at some point I'm going to talk about it later on, but if you have an object, again, from being pushed along a linear path from point A to point B, so we'll call this vector D, the displacement vector. But the force that's being applied is not exactly in this direction, it's actually being applied in this direction. So we have a vector valued force F. Then the work being involved, it's still force times distance, no matter what.